Alright, so in this video we're going to look at some examples of improper integrals. So an improper integral is an integral which involves either an explicit or an implicit limit, which goes to some sort of divergence, either in the bounds or possibly in the integrand. Let's look at this one. Well, this one has explicitly a infinite bound, right? So what do we mean by that? We put an integral from 0 to infinity e to the minus 3x dx. Well, what this means is we're looking at the limit of integrals with upper bounds which go to infinity. So we take the limit as b goes to infinity of this integral. Of course, this we already know how to do, right? So minus 1/3 e to the minus 3x divided by minus 3. That's my antiderivative for that. All right, plug in the bounds. What do I got? Minus 1/3 e to the minus 3b plus 1/3 e to the 0. Now, e to the minus 3b as b goes to infinity, of course, goes to 0. That's equal to 1. So we get 1/3. So what that means is that this integral converged to 1/3. What that means, we add a little something here. What that means, if I can find the right thing, is if we look at, let's see, what does e to the minus 3x look like? Let's see here. Well, it's a decaying exponential, right? So it starts out at 1, and then it goes to 0. Right, as x goes to infinity, so something like asymptotically, right? It never actually gets to 0, but it keeps getting closer and closer to 0. And so what we've just calculated is that the area bounded between the x-axis and the graph y equals minus 3x, which is the red curve, this area here, all right, is in fact equal to 1/3, even though it's got this side down here, which has an infinite length. The height actually turns up a little bit there at the end. That's just bad artistry on my part. This gets closer and closer and closer and closer to the x-axis as we go on, right? And so this graph y equals to e to the minus 3x, despite having an infinite width, right? Its height gets so small so fast that the area is nevertheless bounded and equal to, as we calculated, 1/3. In any of these integrals which we're about to do, similar nature, there's always some sort of corresponding area problem that we're solving, okay? Or it could be that I'm showing that the area bounded by the curve is in fact not bounded, it's unbounded, all right? So here's one. Get this picture out of the way. So this one, sorry, my little one has just woken up. You may or may not be able to hear that, and there's a rainstorm outside too. Exciting stuff, right? All right, so integral from 1 to infinity of dx over x. So what this means is the limit as b goes to infinity of the integral from 1 to b of dx over x. But the integral of 1 over x is natural log the absolute value of x, right? However, in this case, because b is positive and because 1 is positive, the absolute value bars drop out, and we just got log b and natural log of 1, which is 0. Now, the natural log of b, as b gets really, really large, is infinity, and so this is infinity. And so what this says, if you allow me to draw another picture here, is that alright, if we were to look at the graph of 1 over x, and my 1 over x graph is going to look a lot like my exponential. Well, no, wait, excuse me, it will look very little like it. What am I saying? Because the 1 over x, the reciprocal graph, looks like this, right? And there's actually another branch over here. Technically speaking, what this is a hyperbola that's been, it's a hyperbola which opens up asymptotically to the x and the y-axis. I don't know if you ever noticed that or not, but it's the case. And Here's your x, here's your y, right? And the area we just calculated in example 2 would be the area from 1 to infinity. So I don't know, maybe like this to infinity. And despite the fact, by the way, this here, y equals 1 over x. What happens to 1 over x as x goes to infinity? Well, this goes to 0 as x goes to infinity. Just like in the last one, e to the minus 3x went to 0 as x went to infinity. So it's not enough to just go to 0, right? It's got to go to 0 fast enough such that the area is bounded. In this case, it's not. The area under the 1 over x curve from 1 to infinity is in fact infinity, as we saw. All right, let's go on. Next, example 3. I think I need a new cover sheet here. Give me a second. Here we go. This time we're looking at the integral of 1 over x squared plus 1 from minus infinity to 1. All right? So now I'm having fun graphing things. Let me graph another thing here. What's that look like? What's 1 over 1 plus x squared look like? It looks something like, well, 1 over 1 plus x squared is its largest when x is smallest, when x squared is smallest, which happens at 1. And then as x goes to infinity, if you look at y equals to 1 over 1 plus x squared, oops, I did x squared plus 1, which is the same thing, right? That goes to 0 as x goes to either plus or minus infinity, if you think about it, right? So this looks kind of like one of these deals. It should be completely symmetrical. My picture isn't quite right. And what we're doing right now is we're calculating the area bounded by the curve from 1, which would be here-ish. I guess it's more like here-ish. If I'm doing the same scale, this is 1. This is actually 0, 1, that point. So like, I don't know. My picture's probably not quite right, but in here somewhere, there's 1. Minus infinity is not appearing in the picture. So if you just keep going and going and going, we're calculating the area, if possible, bounded by this curve. Maybe it's not a bounded area. Could be an infinite one. Let's see what happens. So, let me get this out of the way. So we calculate the limit as a goes to minus infinity, the integral from a to 1 of that. But of course this is an elementary integral. Inverse tangent, or arctangent if you like, of 1 minus arctangent of a. Now inverse tangent of 1 is pi over 4. Inverse tangent of a as a goes to minus infinity. Well, what's that? That's actually minus pi over 2. Here's y. See over here, here's the graph of inverse tangent, right? Inverse tangent has this graph. And so of course you can obtain the graph of inverse tangent from flipping the tangent graph over. The vertical asymptotes at plus or minus pi over 2 for tangent become horizontal asymptotes at plus or minus pi over 2 for inverse tangent. But anyway, there's the graph of inverse tangent. As you can see, as a goes to minus infinity, we go to minus pi over 2. But then a minus gives me plus, and 1/4 plus 1/2 is 3/4. So there you go. All right, let's go on. So in fact, the area was finite in that example. Example 4, integral from pi over 2 to infinity of cosine x. So we take the limit as t goes to infinity, right? Pi over 2 to t, cosine x dx. That integrates to sine. And then we get sine of t minus sine of pi over 2. Sine of pi over 2 is 1. So you get sine of t minus 1. But the thing about sine of t is t goes to infinity, it's always oscillating, right? So this limit does not exist due to oscillation at infinity, and consequently this integral diverges, right, due to oscillation. So that's a little bit different than the area being unbounded. It's just not entirely defined, right? Okay, next up, example 5. example 5 here. We have the integral from 0 to infinity of 1 over 2 to the x plus 3. So again, the definition means that we take the limit as b goes to infinity, integral from 0 to b of that. So just a side note, odds are very high that your instructor expects you to write this limit and this equality and to write things much as I'm writing here. Part of this course, in fact a lot of this course, is learning to communicate things mathematically, and that's what this notation is for. All right. So don't ignore the notation. Do take a note of it. We do expect you to learn it. Okay. Now, anyway, that said, this is actually that, right? Because 1 divided by 2 to the x plus 3 is really 2 to the minus x minus 3, and then I can integrate this by making a u equals, well, however you want to think about it, but this is the antiderivative. If we differentiate this, we get natural log of 2 times 2 to the minus x minus 3 times the derivative of the inside function, which gives me a minus 1, which cancels that minus 1. So you can easily differentiate this function with respect to x and get back that integrand, which shows me that it's right. Now, if I plug in 0 and I plug in b, according to fundamental theorem of calculus, part 2, I get that. The b gives me 2 to the minus b. Now I took that minus 3 and I made it into an 8. See, 2 to the minus 3 is 1/8. That's where that went. And over here I kept the 1/8 and I put basically I should have done that probably earlier. You can simplify this to 2 to the minus x and put an 8 down here. It's the same. That's what I did here. Anyway, minus a minus gives me a plus from the FTC, like f of b minus f of a, so to speak. Here a is 0. Anyway, I get that. So 2 to the minus 0 is 1, and what do we get? We get 1 over 8 log 2. There you go. This is again a convergent integral. Okay, so an integral either converges or diverges. Them's your choices. Now, they can diverge in different ways, that's true. Some of them could diverge due to oscillation, others could diverge to infinity or to minus infinity. There's a few different ways they can diverge. Here's the next example. This illustrates something called comparison, I think. So check this inequality out here. For x greater than or equal to 1, we have x squared is greater than or equal to x squared. See, if x is greater than or equal to 1, I can multiply. Well, in fact, I could always multiply by x squared. X squared is always for x not equal to 0, it's always positive. So I don't mess up the inequality by multiplying by x squared. Certainly for that, I don't. Excuse me. Goodness gracious. Sorry about that. That'll teach you to put the volume up, won't it? My apologies. All right. Anyway, continuing, we have this inequality: 1 over x, 1 plus x squared is greater than or equal to 1 over 1 plus x cubed, right? So consider this. The integral from 1 to infinity of 1 over 1 plus x squared, just very similar to an example we just did, works out to inverse tangent of something that goes to infinity minus inverse tangent of 1, which is pi over 4. So you get pi over 2 minus pi over 4, which is pi over 4. Great. And then there's this thing called the comparison theorem, which just does a little bit of common sense. It says that if this integrand is smaller than that integrand, as we just argued up here, right? 1 over 1 plus x squared is greater than 1 over 1 plus x cubed, right? And if it's positive, I mean this is positive, right? So I really do need a 0 less than, I do need this 0 here in order to apply the comparison theorem, okay? But I do have that. Then I got that's pi over 4. Well, it follows that this integral is at most pi over 4. So we get that this integral converges. Now I don't know exactly what it converges to, and sometimes I don't care. It's enough to find out that it converges, and that's what this comparison theorem does for us. It tells us that the integral of dx over 1 plus x cubed is less than pi over 4. And that's good news. That means it does not diverge, it converges. All I can really say, though, is that this integral converges, right? Well, okay, fine. I can say a little bit more. I can say it converges to some number less than pi over 4. And that's the comparison theorem. So the comparison theorem is useful for us when we're trying to analyze the integral of some function. Maybe we cannot integrate it, or maybe we just don't want to integrate it. Something like this. And yet it's related to something that we can easily integrate, or we happen to know the integral of. In such a case, we might be able to use the comparison theorem to gain information about the convergence or divergence of something without directly calculating it. This idea we continue to use in future parts of the course, where we deal with series. All right. So, remark, convergence is easier than explicit calculation of a given improper integral. Yeah, it's easier to decide whether it converges or diverges as opposed to direct calculation. All right, example 7. I think this is another comparison example. Let's see what I'm doing. X greater than or equal to 0. We have e to the x squared is greater than or equal to 1. That's because e to the x squared, it starts out at 1 when x equal to 0, and then this is an increasing function. That's easy to show with calculus. If you differentiate e to the x squared, you get 2x e to the x squared, right? And if x is positive, that's positive, so it's an increasing function. So if this starts out being 1 when x equal to 0, it gets larger than 1 as x is larger than 0. And in fact, then, noting that, we can multiply this by e to the x and get this. E to the x plus x squared is greater than or equal to e to the x. Excuse me. It's a simple matter to show that the integral from 0 to infinity of e to the x dx is infinity. All right, this calculation right here does it. So consequently, if the smaller function diverges, the integral of it diverges, then certainly this larger function, which, by the way, I do not want to try to integrate. I mean, we probably could do it if we tried, but it's nice that we don't need to. See, we get that this diverges simply because it's larger than a smaller function which diverges. So these are the two kinds of comparisons that we can do. We can either find a excuse me, a larger function which converges, like in this one, larger converges implies smaller converges, or we can find smaller diverges implies larger diverges. In both cases, we need an inequality linking the two functions in question, all right? And we need to be able to do the integral of the compared function. All right, that moves us on to the next part of this video, which concerns integrals of the other improper type, at least in part. Our next example, you notice there is no infinity in the bounds, right? So what kind of improper integral is this? Why are we saying it's improper? Okay. The reason is, if we put x equal to minus 2 in the denominator, well, then that gives us division by 0. All right. So we don't mean a literal definite integral as we did before. This has to be understood in terms of a limiting procedure. In particular, this integral is understood to be the limit as a approaches minus 2 from the right. This means we consider values of a close to minus 2, but not actually equal to minus 2. And we get closer and closer and closer. This is what the limit is, right? One of those things you should have learned, of course, in, you know what, Calculus 1. All right, so integral from a to 14 of this. Now this we can do with a u substitution. Minus 1/4 power plus 1 gives me 3/4, so I should get a 4/3. Let's see here, scroll down a bit. So we get 4/3 x plus 2 to the 3/4. We evaluate from a to 14. What's that give us? Well, that gives us 4/3 times 16 to the 3/4 power, and we get a plus 2 to the 3/4 power. Now this is a positive power, So when we take the limit as a approaches -2, this just limits to 0. If you had a negative power here instead, that would diverge, all right? But it's a positive power, so when we plug in the -2 here, we just get 0 to the 3/4, and so this function's continuous at -2 is my point. So anyway, this limits to 0, and that is whatever it is. Now that's the 4th power of 16 is 2, so this is actually 8 times 3, which 8 times 4, I think it's 32 over 3. All right, either I was wrong when I wrote this, and I'm wrong now, or we're right both times. Let's vote for me being right. So 32 over 3. Now, let's see here. If I was so foolish as to attempt a picture of this, and that would be very foolish on my part, but I will foolishly attempt it at the moment. Let's see here. It's something like, let's see here, something like at x equals to -2. Alright, so we got 1 over the 4th root of x plus 2, right? So that looks, and this is very, very crude on my part, but it's probably something like this. Let's see here. Oh, let me be a little bit more specific. Plug in 0, what do we get? The 4th root of 2, whatever that is. It's, I don't know, it's something like that, whatever. The point is that this does some kind of deal like this, right? It gets, as x goes to infinity, this goes to 0. We don't get to infinity though, right? We're just going to 14, which I have not drawn enough. Fine. All right, great. All right. You can skip past this part if you want, you know. And there we go. Here's x. Here's my y. I'm looking at the graph for a second here. Y equals to 1 over the square root. Excuse me, square root, listen to me, 4th root of x plus 2. We're just calculating with this integral the area. And see, that's the thing, is the area is kind of sketchy here in a sense. Or at least, let's say, not really sketchy, but it was definitely not defined in our previous experience with integrals, because we wouldn't have talked about integrating the area that's edging up to a vertical asymptote, right? We avoided those things before. Now we are learning how to calculate them using limits. And so I meant to say this is 14. So the area, like that, even though this goes up to infinity, is apparently 32 over 3. Whatever that is, what? About 10.66666666. So there you go, example 8. Let's look at example 9. Example 9 here, another integral of this kind of improper type. Well, it's a little bit different. This one's got a hidden, kind of a hidden singularity. At x equals to 3, this diverges. So we're integrating from -10 to 10, and so maybe it helps to, again, it probably helps to look at a picture. I'm going to keep putting more pictures on my scrap of paper here. So let's see here. So at x equals to 3, this function's got some bad behavior, doesn't it? It diverges to both plus and minus infinity, depending on which side of the graph we're on, right? So this is, you know, y equals 1 over x minus 3 looks like this over here. And it looks like that over there. All right. And we're calculating the area bounded by that graph, if possible, of course. Roughly speaking, up to the limits of my artistry, about from here to here. So the question is it make, what would we calculate the area bounded here? Now, the rule for calculating such areas, the agreement that we have made as a mathematical community is that when we approach this bad point here, we approach the left and the right independently. All right? So that's the first step in my calculation. If you approached the singularity symmetrically, you could have the situation where sometimes it would cancel out due to a certain symmetry. And that might be interesting for certain applications, but that's just not what we mean by an improper integral unless we have another special agreement with the applications in mind, which is not the case here. All right, now, okay, so minus 10 to 3, 3 to 10, this and that. Again, each of these is improper because the denominator goes to 0, either here at the upper bound or here at the lower bound. So those have to be understood in terms of limits as b approaches 3 from the let's see here, from the left, or as a approaches 3 from the right for the upper versus the lower bound. And these give us natural log integrals, both of which diverge. And so that diverges, and when you get like minus infinity for this one and plus infinity for that one, that doesn't mean you get to like cancel them out. That's not how this works. Like I said, these are separate. They're not balanced. And so either one of these blowing up would be enough to kill the whole thing. So anyway, this does not exist. It's a divergent integral. So, and I would warn you that a careless student might ignore the division by 0 and just think that this is equal to that, which is the natural log of 7 minus the natural log of 13, and they would be wrong, right? This type of improper integral requires attention to the domain of expressions. In contrast, the ones that have infinity in the bounds are pretty easy to spot, right? Okay, next example up here. So back to the ones with infinity in the bounds. But this time, something that actually requires us to combine what we've recently learned about integration by parts now with improper integration. So here we go. This is an integration by parts, Udv, and this notation here is a shorthand for a limiting process, all right? So let's see here. So some mathematicians don't like this notation. They would insist on writing like limit as b goes to infinity and then 2 to b here, something like that. And I don't know. But engineers sometimes prefer this notation. But and again, this is not an engineering class, this is a math class, so do please use the notation that I'm encouraging to use here. Anyway, so integration by parts, uv minus integral of v du. And we have to, bounds 2 to infinity. So I'm sticking with this notation. But here's what that notation means. It means the limit as t goes to infinity of this minus that. Well, minus gives me plus. Limit as t goes to infinity of that minus that, right? And so here's a place where students tend to be careless sometimes. This is infinity, and that's e to the minus infinity in some sense. Anyway, it's e to a very large negative number, which is tending to 0. So this is an indeterminate form. It's indeterminate form infinity times 0, which means that you have to do some further analysis of it, right? Now this piece gives me 7/9 e to the minus 6. And this piece I'm rewriting as t over e to the 3t. All right, let me scroll up a bit here. Then this is my notation for L'Hopital's rule on type infinity over infinity. So by L'Hopital's rule, I differentiate the top and the bottom. I get 1, I get 3e to the 3t, and then at this point, this limit's no longer indeterminate. It's just clearly converging to 0 because the denominator gets really, really large while the numerator is just 1. And so there you have it. This is what's left over, and the answer here is 7/9 e to the minus 6. All right. So we could also do this applied problem here. Let's look at it. Find the area bounded by 0 less than x less than pi over 2 and 0 less than y less than secant squared x. If it is finite, also sketch the region. So here's a picture roughly speaking, 0 to pi over 2. Secant squared is 1 over cosine squared, right? So that as pi goes to, listen to me, as x goes to pi over 2, cosine goes to 0. So we got a vertical asymptote in the secant squared graph, like so. And so we're trying to calculate this area. It may or may not be bounded. Let's find out. So this means limit as b goes to, oh no, I forgot to write. So I made a mistake, and then I forgot to, oh, woe is me, woe is me. All right, let's see here. What belongs there? B goes to, looks like pi over 2, and come on pen, you can do it. Pi over 2, and let's see here, from the left or from the right? From value is a little bit less than pi over 2, right? So we put a little minus there. Okay. So then the integral of secant squared is tangent. So we got tangent of b minus tangent of 0 is 0. But tangent of, as b goes to pi over 2 from the left, tangent blows up to infinity there. So this area is actually infinity. The area of the indicated region is not finite. That's example 11 for us. Let's see what example 12 brings to the table. Ooh, work done. I don't think we've done one of these yet. So you may or may not know this, but so in basic physics, work is what? You might have learned, I mean, there's different levels of sophistication with which we can view the problem of calculating work. All right, so perhaps the most rudimentary one is just that work, let me use a different, work is what? Work is equal to force times distance. But in order for this to make sense, we need the force to be constant, and we need the distance to be in the same direction as the force is applied. All right. Thinking about the force being applied in a different direction than the displacement, or the, well, that requires the technique of vector analysis. We'll talk about that in Calculus 3, perhaps. Now here, if the force is variable, though, we can think about the little bit of work being done by a force at x, a displacement, a little dx here. So I think about a picture something like this. We're going from x to maybe x plus dx, just that little displacement. And going from here to here, you might think about the force being, right here it would be f of x, right here would be f of x plus dx, so to speak, but dx is so very tiny that essentially it doesn't matter if I use this one or that one. The force is essentially constant over this infinitesimal displacement. So the little bit of work done over the displacement dx is just f of x dx. And then if I want to find the net work, I integrate dw, I add it up, right? And so that's the idea in this example, is we can integrate, and the integral of dw really just means the integral of f dx over the appropriate region, over the appropriate bounds, as I'll talk about here shortly. So to calculate the work done by a variable force, we just need to integrate it, and that makes a lot of sense because of this little discussion. All right, anyway, here we go. So let's calculate the work done from x equals to a to x equals to b. Well, that's given by this. All right, so there it is. I tried to explain to you why that's true, but there's the formula. So this is a one-dimensional force in motion, and we're going to be looking at the force on a charge q due to a charge big Q by Coulomb's force law, which is qq over 4 pi epsilon naught. This is the permittivity of free space times r squared. I think 4 pi, well, 1 over 4 pi epsilon naught is also sometimes denoted k in physics. It's, goodness gracious, I forget what its value is, maybe 10 to the 9th or something. Anyway, you can look that up, but again, property of space-time, of the vacuum, this permittivity of free space. And I'm assuming that the charges are both positive, so that means that the Coulomb force is repulsive. Here's a picture. And so we're going to, well, I'll explain what the calculation is as we go on here. I can't fit it all on the same screen at once. So we're assuming that, suppose that this charge Q is initially very, very far away from big Q, and then it's moved radially in from its initial position to a final position of R equals to R from Q. Then the question is, what's this work done? What's the work done by the Coulomb force, right? So we're taking Q from way over here and moving it until we get to little r equal to big R, wherever that is. Maybe it's here. The question is, how much work does it take to move the little q from, let's say, infinity, which is very, very far away, to a finite radius r? Well, here's the calculus for that. All right, we're going to integrate from infinity to big R of f of r dr. That should give me the work done by the force going from infinity to r. Now, I flipped the bounds and get a minus, right? So minus r to infinity of that. Then, this is improper integral. So we take the limit as b goes to infinity from r to b of dr over r squared. This is a constant, so just pull it out. And this integrates to minus 1 over r. Then that's minus 1 over b, minus a minus 1 over r. This goes to 0. That leaves me 1 over r. And there you have it. Minus q over 4 pi epsilon naught r. You might recognize the q over 4 pi epsilon naught as the formula for the voltage of a point charge, assuming that the voltage is 0 at infinity. If you didn't know that yet, you'll learn it in another course at some point maybe. But there you go. The work is negative because the force was always opposite the direction of motion. In any event, another force would be needed for this motion to occur. And by the way, if the net force was 0 during the motion, then the other force would be the same magnitude as F, but in the opposite direction. On the other hand, if the net force was not equal to 0, then Q would have some kinetic energy when it reached R equals to R. But I will leave the rest of this kind of discussion for your course in physics. For us, it's enough for us to just, given a force, calculate the work done. That's, again, just a basic application of integration. And this idea I was showing you a minute ago about, taking an average idea, force times distance, and implementing it at the infinitesimal level, and then taking an integration to add up the infinitesimal bits. This is part of what I would refer to as the infinitesimal method. I'll be talking more about that as we go on. The fundamental guiding principle for setting up applications is this infinitesimal method. Anyway, I think that's it for this one. So thanks, guys.